All right, everybody, welcome to our first application problem Zoom class. So I picked a couple of problems that were similar to the ones that were assigned. Hopefully this helps. The first thing I want to say is, remember, this is a math course. This is not a physics course or an engineering course. Although it is for engineers, it is a math course. So the most important thing that you learn in this course, in my opinion, I guess I should say that, is the math. So Edfinity is where you'll look. I will give you a lecture on the math part. Please watch that. Then you'll do your Edfinity homework, which will help reinforce the mathematical principles that you will be using. And then the last thing I think to do would be to go to the word problems or the application problems. I am also aware of the fact that most people are very frightened of word problems. So I'm going to try to walk you through them, tell you what to look for. The problems themselves are not very difficult once you see how to read them. So let's begin. The spring force F and displacement X. So those are being told to you because we're going to be given these letters and we need to know what they represent. So always make sure you understand what F is, what X is. So the spring force is F and the displacement is X. And if you want, you could even just highlight it if you have a piece of paper and a highlighter. Okay. So for a closed wound tension spring are measured as in figure 1.3. Okay, so that's a picture of the tension spring. We are given some data over to the side of it. I don't know what to do with that yet because we haven't seen a question, but I am reading it. As you notice, I'm reading it really slowly. I'm not reading it like it's a novel. So these are not novels. These are word problems. You have to read them very, very carefully and slowly to make sure that you understand what each sentence has in it. And sometimes you'll be given information that you don't need. You also need to figure out what it is that you may not need. So let's read the rest. So the spring force F and displacement X satisfy the linear equation where K is the spring constant. So we're being told that K is constant. Again, another very important thing. So it is not variable. It is not changing. It is a value. It could be 2. I don't know what it is yet, but it is a number. And F sub I is the preload induced during manufacturing of the spring. So it's basically how hard it is to pull the spring. Okay, that's what the spring constant usually is. Okay, so A, use the given data. Where's the given data? Oh yeah, the given data is right here. Okay, to find the equation of the line for the spring force, F as a function. So again, something's really important. F as a function of X. And let's say we have the equation that looks something like this. This is not the equation of this line, I promise. But let's say we have something like this. F of X means F as a function of X. If I want F as a function of time, so displacement is distance. So this is going to give me something that's going to show me some distance. But I might have another type of question that asks me something as a function of time. So all I'm saying is that now I would have F of t, and this would be t, where t is time. This is called the independent variable. Why is it the independent variable? It's the independent variable because that's like if I pick t equals 1, then I get my f of t, which is really the same as y, right? This is called the dependent variable because it depends on what I pick for x or t or whatever it is that I'm picking. Okay, so now we know we have a function that x is the variable that we're using, okay? So this, and here we have it. Here's my x, and this f is really the same as capital F of x, okay? And determine the values of the spring constant k and preload f sub I. Okay, so how are we going to start this? Well, let's start it by saying we know the equation of the line is going to be f equals kx plus f sub I. Okay, so why is that a linear equation? Well, a linear equation in slope-intercept form looks like this: y equals mx plus b. And here we have f equals kx plus f sub I. So hopefully you can see that these are similar and that my function, my y value, which is the same as my f, my k is the same as my slope, right? It goes in front of the x value. Let's do this. K is the same as m, and f sub I is the same as my b. So if you know what y equals mx plus b means, then now we know what f equals kx plus f sub I means. So the first thing we would do is, well, I have to find m and b, because eventually I need to have something of this form, right? Y equals something, f equals something, f of, it doesn't really matter. They're all still linear, okay? So if I look here, what is it that I can do first? I need to find k and f sub I, which is the same as m and b. I look around and I see, oh, I have some data points here. So if I have 2 points, these are really the same. This data is really the same as 2 ordered pairs, 25, 135, and 50, 222. So I have 2 points. That's all I need to find the slope. So now I can find the slope. I can say m, which is equal to k for the equation that we're looking for, is equal to y2 minus y1 over x2 minus x1, right? Rise over run. And again, it doesn't really matter what you call, which I'll call this 1.1 and I'll call this 0.2. So what I get is y2 is 222 minus y1, which is 135, divided by x2, which is 50, minus x1, which is 25. And then if we take out our calculator, I actually already have the number here somewhere. I think it's 87 over 25. Yeah, so this is 87 over 25. And then if you were not allowed to use a calculator, that would be sufficient. If you're allowed to use a calculator, then what we're going to do is use a calculator, and we can say this is equal to 3.48. You can definitely use calculators on your homework. I would use your calculator as little as possible. Now we found the slope of the line. This was our slope, which was the same as our k. So now we've started creating our equation. We know that f equals 3.48 x plus f sub I, okay? But again, I don't know what f sub I is. Well, that's okay, because I have two data points right here, and I could plug them into my equation and find f sub I. So let's do that. And I'll just use the top one. You can use either set of data. F is equal to 135, which is equal to 3.48, times x, which is 25, plus f sub I. And then I get out my calculator, and I have 135 is equal to, so this is 87 plus f sub I. And then I subtract 87 from both sides, and I get 48 is equal to f sub I. So now I have my entire equation. F is equal to 3.48 times x plus 48. So this is the answer to A, I believe. So A says, using the given data, find the equation of the line for the spring force F as a function of displacement x. Okay, we did that. This is F as a function of x. And determine the values of the spring constant K and F sub I. Well, we had to do that, or else we wouldn't have been able to find the equation of the line, because K is the spring constant, which we found first by using the slope formula, and F sub I we found second by using the values in the table. So I would say that the best thing to do at this point is just to make sure you write K equals 3.48 and F sub I is equal to 48. And this would be everything that they've asked for and answered and put in the form of a function. Okay, now I do have room. I can see it on the side here. I have room, so I'm just going to scroll down, because part B says to graph it, I believe. So sketch the graph of f as a function of x and clearly indicate both the spring constant k and preload f sub I. So we can see that these numbers are going to be kind of big. For example, when I look at the values that I have here for x and y, they're going to be 135 and 222 and 25 and 50. So I can't really make those tick marks small. So I'll make some tick marks here. And since our x values, this is our x-axis, since our x values right now we know are 25 to 50, why don't I make these 10 each? So 10, 20, 30, 40, 50, I'll go to 60. And since our numbers for our y values or our f values are up to 200, I think what I'll do is I'll make these in 50s. So let's make this a 50. We can make this 100, 150, 200, and 250. Okay, so our first point is 25, 135. So 25, 135, let's say that's right about there. And our second number is 50, 222. So let's make that right there. And actually, it's going to have to go through 048 because that's our y-intercept. So let's kind of move it so that it does that. There we go. So now there's the equation of my line. Get rid of the ruler. And it starts here at 0. So f sub I is 48. That's our y-intercept. I'm assuming that's 48. And then you can see that the other 2 points are on the line. If it was even more perfectly set up, if this was really to scale, it would be even better. But not too bad, actually. So let's just make sure we did everything, sketch the graph of f as a function of x, and clearly label both the spring constant k and the preload f sub I. Well, I did not label anything. So I can label this point here on my graph. This is f sub I because it's the initial position of the spring when x is 0, when there's no displacement. That's the initial force. And our slope, maybe the best way to show our k is as the change in y over the change in x. So our k is equal to delta y over delta x.